Okay, let's discuss a simple power cycle. This is not really an example. I'm just using numbers from the back of the book with through the tables. And I want to explain conceptually what's happening here. So this is one of two cycles we can kind of study in great detail without mastery of the second law. So after we do the second law, we could do a lot more than just this. But at the moment, we can still do this and talk about this meaningfully. So we have a cycle, meaning that it goes around in a loop. And so, it doesn't really break. The idea is that you have steam. This is all steam. And you have different conditions. So let's kind of discuss what's happening. Over here, I have a pressurized steam at a high temperature. And so this is going to be a superheated steam. So as far as the states go, I'm just going to denote that in blue. This is a gas. This doesn't look like a G. This is a gas. Okay. And here, after it goes through the turbine, and we'll discuss what the turbine does again, it changes its pressure and its temperature and its volume. All things will change. And as a result, I get, and I didn't write that, I get a saturated liquid steam mixture. And in this particular case, the quality is 0.9. We're going to have some sort of quality here. So this has both the gas and a liquid state in here. Then after it goes through a condenser, it stays at the same pressure and temperature. And it just converts itself from X is 0.9 to X is 0. So meaning this is just a saturated liquid at the same prevailing conditions. And then after it goes through the pump, this is a liquid. It's going to stay a liquid up here as well, just has different conditions. Okay, so that's kind of like what's happening here. And this is kind of hard to see. And let me walk you through what's happening more intimately. So into the boiler, I have to input heat. So Q boiler. Into the pump, I have to input work. Okay. Out of the turbine, I will get work, which is what I want. Work turbine, T. And out of the condenser, some heat will release as well. QC will say. Okay, so that's sort of what's happening. So basically, we'll think about it this way. And even though they're labeled 1, 2, 3, 4, imagine we feed it in initially at state 3. So we charge this thing at state 3. And you can see this is a pressure of 0.3 bars. It's not so far from our prevailing pressure. Atmospheric pressure is about 1 bar. And a temperature that's kind of attainable of 69 degrees. So we can put that in. And it's a liquid. So we put in liquid water at 69 and 0.3 bars. You can even design that so that it's P atmosphere and the temperature will be 100, however you want to do it. So you have 100 degrees Celsius or something like that. You have saturated liquid water. And there's no vapor in this thing. Then we're going to feed this into a pump, and we're going to put some work into that. So, maybe we put in, plug it in somewhere. Maybe we spin something to give it some extra work, or whatever have you. We put some work into the system, into the pump, and the idea is that the pump, maybe we put a battery, whatever you want. We put a pump work into this, and what it will do is it will take the saturated liquid and it will bring it to another state where it's still a liquid. And you can see that the volume does not change because it's an incompressible liquid, and the volume will stay the same and the temperature will stay the same. And what we're doing through this work is just pressurize this thing. So we put this at a high pressure. So we're going to pressurize our liquid water into a higher pressure, okay, and see T and V stay the same. Then what we're going to do is we're going to put some heat. Maybe we put some gasoline into this that releases chemical heat that will heat it up, or maybe we put it on the fire, or whatever have you. We have to input heat into a boiler to take this liquid and vaporize it at the same pressure. And at this time, what happens is that the temperature goes way up from 69 degrees to 520. So it goes up. So now I have a high pressure steam. And basically you could think of it as sort of like a spring, right? And it's kind of like mushed in together, and you kind of condensed the hell out of this, and it's inside of a cube. So imagine you have this cube here, and you condensed steam inside of this. So obviously what it wants to do is expand beyond that, but you're restricting it. So you're putting some sort of a potential energy barrier onto this. And what you're doing in the turbine, so the turbine, you can see it has this kind of schematic that basically you're going from a condensed state to an expanded state. You're allowing this thing to expand. And in the turbine, you're going to have some blades like that or something. And, you know, I'll do another one. Something like that. Maybe I have blades in the turbine, and you basically like this because it's expanding. And so you're introducing this cube that's got a lot of potential energy because all this vapor is stuck in, not vapor, all this, all this condensed steam is stuck in it. And you're allowing it to expand. And as it's expanding, it's going to move through. And as it's moving through, it's going to move and make these things spin. And if they're attached to something, you can extract work out of it. And it's going to spin and go out here to a place where now it's expanded in volume. And you can see it really ballooned in volume here from V1 of 0.0039 to V2 of 4.7. So it really went up a lot by several orders of magnitude, went up. The temperature decreased as a result, and the pressure obviously decreased as a result because you're not pressurizing it anymore. The temperature kind of went along for the ride, but obviously, intuitively speaking, the pressure should go down, the volume should go up. What results is a saturated mixture of gas and liquid, and it just happens to be in this particular example that it's 0.9. It could be 0.8, 0.7, 0.75, whatever. And these conditions can be a little bit different. But the idea is that the pressure goes from something really high to something really low. And this low is kind of around 1 bar, maybe a little bit below, and temperature is something that's attainable. Okay, so you don't want to touch it obviously at this state, but anywhere else, it's a little bit more manageable to kind of carry around. Okay, then what you do now is you generated work. So you could do something with this. So if this is like an electric generator, now you generated work and you can do something with it. Okay, and the idea for a cycle is to kind of repeat. So what you're going to do now is prepare it to, you're going to recover it. So what you're going to do is, well, you can treat stream 2 directly to go to stream 1. The problem is that stream 2 has got some gas in it. And why is that a problem? Because gas takes up a lot of space, and this is a lot of space. So you don't want to handle that. You don't want to have to deal with this for three different iterations through the condenser, the pump, the boiler. So what you do is you're going to condense this thing, meaning you're going to make the volume go way down by getting rid of all the gas, because liquid has a lower density. So you're going to cool it off through a condenser. You're going to allow this to release some heat. And as it is releasing heat, staying at the same temperature and pressure, is going to release heat adiabatically, and it's going to go to saturated liquid only, and then this thing repeats again. So you can see the volume went way down, and now we can repeat. This is more manageable and cheaper to kind of handle than having to deal with this. Meaning that if I were to take this directly and skip the condenser, the work that I would have to put to the pump would be higher. So this cost me money, this cost me money, and this gives me free work. So the idea for this is to compare how much work you get. So work from the turbine, if you divide that by work to the turbine, and you can subtract the work from the pump because you have to put that in. So the net work will be that. If you divide this by the heat that you have to supply to the boiler, okay, and you multiply this by 100%, this gives you a measure of efficiency, how efficient this thing is. And you will see that for the most part, what you will get is something on the order of 30 to 40%, something like that. Doesn't have to be, it could be a little lower, higher, but you know, around this kind of area. meaning that you're going to put in a ton of heat and you're going to get only 30% of that heat into work. Now, why should that matter? So work pump in this example, just to tell you, if you work it out, and we will do this in greater detail with actual numbers. If you work this out, the work for the pump, let me show you, the work for the pump ends up being negative 10. So we'll say absolute value. You have to supply 10.2 kilojoules per kilogram. The heat for the boiler, you have to supply a lot, 3126 kilojoules per kilogram. See, and then the work that you actually get, which will be positive for you, is going to be 1033.4 kilojoules per kilogram. Okay, so you're going to generate this, which is great, and you can do stuff with this. That's what we want. You want to maximize this at the expense of this. Now you can see you're not putting so much work into the system. Your greatest penalty is the heat that you have to provide to the boiler. This is kind of manageable. This one is really the pain, and you could see that your efficiency, if you kind of carry this out, is kind of low. So in this particular example, if you work this out, I think you get an efficiency of about 32.7%. Not great, but you could see that basically what you did is that if you kind of ignore the work of the pump because it's kind of small, the heat of the boiler, you convert about a third of it into work. So you convert heat into work, and that's the idea of this power system. So you can power cycle, so you can have a way to generate work for you from heat, not from work. It's not like you're converting work to work, because otherwise you just plug this into the whatever you want. This is not much. This is only 10 kilojoules per kilogram. This gives you 3,000 or so. No, sorry, 1,000 or so. So it's 100 times bigger. So you want to have, this is the kind of the motivation behind having this. So this is kind of the mechanics behind it. What we're going to do is really discuss this through an example, and I will give you a way to kind of determine these numbers. So your goal whenever you see a question or a problem having to do with a cycle is basically you're going to have to calculate the work of the pump, the work of the turbine, the heat that's going into the boiler, and also the heat that's released by the condenser, which in our case is negative 2100 or so. So you can kind of, so I'm giving it to you by way of, you can also kind of figure this out now with the numbers if you want to, because I'm giving you all the numbers, but I'm just kind of sketching this out. So again, so what you're going to do is you're going to basically determine these four numbers. You're going to calculate the efficiency, and you can kind of try to sketch out what the states are. Usually that's your first step, like in any thermal question, state the states. And after you state the states, you can do first law and then eventually also second law analysis, and you can get the work and the heat and the efficiency, etc.